My name is Daniel McDonald. I am the lead developer for the synthetic geometry team here at Wolfram Research, um, along with my colleague Peter Behrens, who has another video uploaded. We will be giving some updates for the synthetic geometry project in the Wolfram language. I will be introducing the new kernel function GeometricSolveValues, and Peter will be talking about updates for FindGeometricProof. We also encourage you to check out our colleague Xiangwei Yang's separate talk that involves some synthetic geometry functionality. So I'll be talking about the function GeometricSolveValues, which is will be appearing new in version 14 in a few short weeks. And so GeometricSolveValue takes its input, a geometric scene and some expression, and it solves for that expression, which represents some quantity in the geometric scene. So let's take a look at some examples. So as our first example, in most of these talks, I like to use Thales' theorem. So Thales' theorem, we have a geometric scene, and we have a triangle and the circle that goes through the vertices of that triangle. And we specify that one side of that triangle is a diameter of that circle. So we can use our function RandomInstance to visualize Thales' theorem. So here we've got our circle going through the vertices of the triangle, and one side of the triangle goes to the center of the circle. So GeometricSolveValues, can work in sort of two separate ways. One way is we solve for something for a particular scene instance. So for this particular scene instance, we're going to try to solve for the angle at this point B here. And if we do that, we just get a numerical value based on the scene, and it looks like it's about half of pi. If we want to solve for this angle at B in general, so this is not based on this particular scene, but just based on our abstract scene, then instead of inputting this particular scene instance, we just input the abstract scene for the first argument. And in fact, we do get pi over 2. So so GeometricSolveValues can solve for a particular instance or for a scene in general. So let's look at another example. So now let's consider a new scene where we've got one point C that hasn't fully been specified. It's got a y coordinate, but we don't know the x coordinate. We just know it's positive, and the other points in the triangle have been specified. So let's visualize this. So our point C here has x value x and y value 5, and we are interested in the area of this triangle ABC. So again, we can look at this particular instance, and it's easy enough to find the area. We just do it numerically. but we can also find an expression for this area in any value of x. And so here we get 2x. So let's move on to a third example. So here, let's look at a scene featuring a right triangle where we know the leg lengths, but not the hypotenuse. So again, let's visualize this using RandomInstance. Right, so we're given that that AB has length 1, AC has length 2, and then H is this Euclidean distance, aka the hypotenuse. So the subvalue algebraic formulation of a geometric scene object gives a conjunction of constraints for that scene to be valid. That is, so if we take this subvalue algebraic formulation of the scene, we get this conjunction of constraints for this scene to hold. So to find this hypotenuse, we can run the existing function SolveValues on this algebraic formulation, or we can run our new function GeometricSolveValues directly on the scene. And in fact, we get the same results. So just to be clear, running SolveValues on the algebraic formulation is not simply how GeometricSolveValues works. Most complicated scenes running SolveValues on the formulation will take longer than you'd like to evaluate. No fault of SolveValues. It's there just can be much more complicated algebraic formulations than this. So in general, I wouldn't recommend it. GeometricSolveValues does some chicanery behind the scenes to speed things up. Okay, so now let's look at a few more complicated examples. So let's solve for the area of a triangle. Right, so we've got this scene where we have these lengths specified and also specified the relationship between these two angles, and we would like to solve for the area of this triangle T, in general, not just based on this particular scene. So if your geometry skills are sharp, then perhaps you might like to take a look at this notebook and try to work this out on your own. But if your geometry skills are not sharp, or you're just a little bit lazy, you can run GeometricSolveValues on this and see that the answer is 33. So we do get an exact answer for the area of this triangle. Let's try another example. So here we've got a quadrilateral. We can look at this picture. So what givens do we have? So we've got, we are given a couple angles and a relationship, a perpendicular relationship between two lines and a few distances, and we want to find the area of this this polygon P. And so again, I encourage you to see if you can work this out on your, go back to this slide and see if you can work it out on your own. But if you don't want to, you can see that the answer in general is 48 area units, or 48 length units squared, I suppose. Let's see, and then let's solve for an angle in this figure. So we've got we are given 100-degree angle here, and we're shown that the distance between A and B is the same as the distance between B and C. And then we're also given a couple other angles. So at A, we've got 30 degrees, and at QBC, which is here, we've got that this little angle here is also 30 degrees. And we are looking for this angle APQ, which is right here. So again, I encourage you, if you're geometrically inclined, to go back to the slide and see if you can work this out on your own. But if you don't want to, or want to check your work, you can run GeometricSolveValues and see that, in fact, this angle is also 30 degrees. And our final example for this part of the talk, we're going to solve for the distance between 2 points. So we've got this quadrilateral, and we've got a few of these angles specified as right angles. So right angle here, and right angle here. And we're given a few distances between points. So we've got AE is 6, BF is 6, ED is 3, and AB is the same as BC. So we've got AB and BC the same distance, and we are looking for the distance between A and C, so the length of this orange line. So again, see if you can work it out on your own and get the answer, which is 18. All right, so GeometricSolveValues, as you see, just gives you an answer if you're actually interested in how to prove these things using Wolfram Language. Then you should learn about FindGeometricProof from my colleague Peter Brenz, who will be coming up next in this talk. Thank you.
Greetings, fellow geometers. My name is Peter Behrens, and I'm going to give an update on the resource function FindGeometricProof. This has been discussed at previous tech conferences. It's still under development. Basically, FindGeometricProof takes in a GeometricScene object and produces a proof. It includes many different properties and representations of the proof, but the most interesting one is the human readable proof that takes the form of a classic 2-column proof that is aimed at the high school level geometry student. FindGeometricProof uses a collection of elementary synthetic geometry theorems as its axioms, uses those to produce more and more conclusions. the first way to use it would be to give it a geometric scene, and in the first argument, give it a specific assertion that you'd like to prove. So this could be anything like the Euclidean distance from point A to point B is equal to 10. It could also be something with units. It could also be something with a pattern in it. And that would be telling it to find the first instance of a fact, or return the first proved instance of a fact that fits that pattern. Alternatively, you can use the all keyword in the first argument, and that just tells it to produce as many facts as it can from the geometric scene, which could be quite a lot, as you can imagine, depending on how complicated the scene is. It can also, given just a geometric scene, try to prove the conclusions, which are that third argument of the geometric scene, that optional third argument. Now, there's a lot of different options which are useful to sort of hone the kind of behavior you want, especially when it comes to using very complicated geometric scenes that can potentially produce a lot of facts, a lot of which may be not very interesting. The proof object that results contains a lot of different properties. We have many representations for it: a computable version, a data set version. Augmented scene and scene with conclusions are two ways of taking the facts that have been proved and recycling them into a geometric scene for further use, say, with RandomInstance. There are two graphical representations of the proof graph and the proof graph manipulate. The proof notebook is that classic two-column proof that at least U.S. high school students are used to, and of course the length. So a very easy example, we can just find the base from an area and an altitude. In this case, we have units of meters. We're given a line, a distance, and an area. But if we put this scene into FindGeometricProof and ask it to prove that the length of the base, that is from Y to Z, is a certain number of meters, it will find that proof. We can ask for the result property, and we get that exact distance fact in this case. And the proof notebook, here we see this kind of two-column proof. Each fact is numbered, it's given a reason, and each reason references previous facts by number. Here's an example of using the all keyword. Here we have a basic scene where we just have three parallel lines and then a transverse line, and we're given exactly one angle. Here we've got the random instance of the scene. If we ask to prove all facts, in this case, we're given 21. It could often be much more, and it could even go on for a very long time. But this is just simple enough that it doesn't prove too many things. It gets all the angles it can, and then it finds some of the relationships between the angles that it can't find. Looking at the proof graph, we have some nice features such as tooltips for the inferences. Each fact is labeled with a vertex, and the given ones are noted. Another thing we can do is to play around with the axioms that are allowed to a specific value of that option called full trigonometry, and that just allows the additional axioms of trigonometry. So if here we have a scene that's a triangle, but it's not a special triangle for which we would not need trigonometry. It's just a sort of a random triangle with two angles and a distance. And if we just run FindGeometricProof to find the area as a real, it will fail and give us this failure object. Although we could ask for the partial proof, and that will give us a few steps, which we could then look at the proof notebook and all the other properties that the proof object has. But if we set the geometric axioms option to full trigonometry, we can actually get the proof. And if we look at the two-column proof, you see that it uses the law of sines to begin with, And then it uses Heron's formula. Once it knows all three sides, it can find the area. A more advanced example is here, where it might not be so obvious how we get the distance from C to O. So we ask for a numeric value. In this case, we have a pattern because we don't know the answer already. If we didn't specify that it was numeric, it might give us something that we don't want, like the distance from C to O is equal to the distance from B to C or something. So we want a numerical value. In 14 steps, it finds the result, and the result is 15. And if we look at the proof notebook, we can see that it uses Ptolemy's theorem on cyclic quadrilaterals and some algebra on some of these previous steps to get the final result. Thank you for listening.
All right. So that is our talk. Unfortunately, Peter is a bit under the weather today, so I'm Dan from the first video. I can continue answering answering questions in the chat. It is let's see, I feel like right, so I think I'm the only one who's able to speak, so I'll keep answering questions in the chat until 2 o'clock, when hopefully you go to your next session. So anyway, previous questions had to do with whether there's a 3D version of this coming out, and that's sort of our next project for the synthetic geometry is for our next big project is to allow for sort of an interactive construction method for geometric scenes. So rather than having to code it, you can sort of have a palette where you sort of draw your own lines and circles, and we figure out the relations that you want to hold among your structures, and then we create a geometric scene based on that. And then sort of after that, our next major project will probably be something like GeometricScene 3D, which will be a major undertaking and will maybe require a few new computational techniques, because that will be rather computationally intensive. Let's see, and Bruce just asked a question. These capabilities are clearly valuable in the classroom, we hope so. Are you aware of their use outside the classroom? I will say that as far as random instance goes, this is what's technically known as a geometric constraint solver. And so geometric constraint solvers outside of the classroom are actually used in CAD drawings. I feel like we will be, if we get the geometric scene 3D working, I think that will be quite useful for CAD drawings. I think there are some some uses for the current geometric scene for 2D CAD drawings, but I think it will be quite useful once we can get it into 3D. As far as the next question here about adapting our scope to hyperbolic geometry or non-Euclidean geometry, we've gotten that question before. That project would, if that happens, would would happen after we got the GeometricScene 3D working. So I think 3D Euclidean geometry would happen before that, and along with our 3D GeometricScene 3D is presumably what that would be called. We would probably want some other sort of palette for constructing those. And then once we get done with that, then the next major project would be looking into the viability of non-Euclidean geometry. So non-Euclidean geometry is on our radar, but that would be very far down the line because we're about to release version 14, and in the ideal world, we would get this palette for the current geometric scene in by version 15 maybe, and then have some version of GeometricScene 3D for version 16 maybe, and then if we did non-Euclidean geometric scene, that would be probably version 17 or 18. So that is quite far down the road. It's been on our radar, but there are some, that will be, there's some, there's a lot of design work and computational experiments that we'll have to do before we can get get non-Euclidean geometric scenes working. Let's see. Right, so we have the geometric scene constructor in Wolfram Alpha Notebook Edition that can be used in Mathematica. How is that different from what you said in your next project? Right, so that is actually sort of a halfway step to our next project. So one, we'll be sort of tweaking the design of that to get that in the kernel with this. But sort of the big project will be something more like you would see with GeoGebra, or some of the other existing geometry functionality, where rather than like click things off of click text buttons that say, okay, I want a circle or something, you would actually have something where you could draw a circle. So something a little closer to to the drawing programs, to actual drawing programs where you'd have circles and lines, and you actually are placing the circles and lines where you want to, and then perhaps you can add some implicit constraints if you want, but sort of drawing a geometric scene yourself, and then we figure out what the actual coded version of that geometric scene is if we want to plug it into any of our functionality. So yes, you are correct that this geometric scene constructor is sort of our first step in this avenue. And we do hope to, after some design reviews, we do hope to get that into the kernel first. And then we would work towards these actual drawing palettes.